Hello, everybody. This is lecture 16.2 on direct proportionality and inverse proportionality. All right, in each of these videos, we've done kind of a little overview of the lecture. In this one, we're going to do a sort of a preview, and that's kind of a justification for why we're taking on this topic and what this has to do with gas laws and why this is going to be useful for us. The state variables of gases are the properties that, are the things that describe the properties of a gas, right? And there are four of them: pressure, volume, temperature, and amount of gas, or number of moles of gas. And every textbook has a section that talks about simple gas laws that relate each of these variables to one another in pairs. And there's a lot of textbook space devoted to doing calculation for pressure as a function of volume, or volume as a function of temperature, and so on and so forth. Okay. What we find, though, if you look at any of these, this particular pair of variables, pressure and volume, are related by what's called Boyle's law. And if you go in textbooks or go online and look up Boyle's law, you'll find that the relationship between pressure and volume can be written in a whole bunch of different ways. One of the more common ways you'll see this is P1 V1 equals P2 V2. You'll sometimes see PV equals K, or P equals K times 1 over V, or V equals K times 1 over P. And the same thing is true for all of the other different pairs of variables. You take any pair of these, and there's a whole bunch of different ways to write that relationship. And this, to me, is very confusing. And I think it's confusing to a lot of students also. But what I'm going to tell you is that every single one of these pairs of variables is related by a certain relationship, which is either a direct proportionality or an inverse proportionality. And so if you understand direct proportionality and inverse proportionality, then you don't have to worry about any of these equations anymore. And you can immediately derive your own equation and figure out your own math for describing the relationship between any of those pairs of variables. And that's our goal here, because I really would like to get away from memorizing equations and move toward understanding everything in the simplest possible way, and then using that simple understanding as a way of taking care of mathematical problems. All right, so let's take a look at this. All right. First, we're going to look at direct proportionality. You may have talked about this in, in school before you got to college. You probably didn't know it was going to come back up again. And direct proportionality is just a way of describing a relationship between two variables or two properties. Two properties, x and y, are directly proportional if an increase in x results in a proportional increase in y. And the same thing is true for a decrease in x resulting in a proportional decrease in y. So what that means is, for example, if property x doubles, then y also doubles. If x triples, then y triples. If x is increased by a factor of 10, then y would increase by a factor of 10. It also has to be the case for something to be directly proportional that when x is 0, y is 0. So if the amount of one property is 0, then the amount of the other property is also going to be 0. So here are a couple of simple examples from daily life, right? Buying fruit, right? If you go to the store and you buy a pound of apples, it might cost $2.49. If you buy 2 pounds of apples, it's going to cost $4.96, twice as much. If you buy 5 pounds of apples, it's going to cost 5 times as much, right? So the cost of the apples is directly proportional to the amount of apples that you buy. Right? Same thing is true for hourly wages, right? If someone is working and earning $15 an hour, if they work 1 hour, they get $15. If they work 2 hours, they get $30. If they work 4 hours, they get $60, and so on and so forth. The wages that they take home is directly proportional to the number of hours that they work. Okay. Now we can look at this mathematically. Start with a simple graph. If x and y are directly proportional to one another, then we get a relationship that looks like this. Right? As x increases, y also increases. Right? If you double the value of x, you double the value of y. Okay? We can write a mathematical statement for this in 2 ways. We don't typically use this one, but I just want to put this out here because you sometimes see this. This little symbol here that looks kind of like a fish or a Greek letter alpha is a mathematical symbol which just means is proportional to. So you can write the statement this way: y is proportional to x. Normally, a more useful algebraic statement is to write it this way: y is some constant times x. That's how we'd usually write this statement. And notice that if we're looking at the graph here, right? Let me put this here actually first. K is a constant. Okay, and also in that graph to the left, oops, K is the slope of the line in the graph of x versus y. All right, now let's look at how we can use this to solve a problem. All right, so let's take a look at a fairly simple problem. A particular car can travel 56 miles on 2.7 gallons of gas. How far can the same car travel with a full tank of 16 gallons? Well, it seems pretty intuitive, I hope, that the distance that you can travel is directly proportional to the amount of gas you have. If you've got twice as much gas, you can drive twice as far. If you've got 5 times as much gas, you can go 5 times as far. So if that's the case, then we know that the distance is directly proportional to the amount of gas. And if the distance is directly proportional to the amount of gas, then we could write a simple equation like this, where D stands for the distance and G stands for the amount of gas we have, and K is some constant that we don't know, but which we can figure out if we need to. Okay. So if we recognize that there's a direct proportionality, then we can write this mathematical relationship, and once we've got that mathematical relationship, it should be pretty easy for us to solve the problem. Okay, we're going to look at 2 fairly simple ways to solve these problems. And the first one is what I'm going to call the 2-step solution, because it takes 2 steps to work through the math. It doesn't really have anything to do with dancing. We've got Steve Harvey doing his version of a really nice 2-step. So you don't actually have to dance in order to solve problems this way, but I do find that it helps, and I highly recommend it. The second method is what I'm going to call the isolation of constants. Okay, we're going to take all of the constants, put them on one side of the equation, and put all of the variables, all the things that are changing, and put that on the other side of the equation. And then we'll use that to solve mathematically, and it'll should be pretty straightforward. Let's take a look at an example. We'll do a two-step solution first. All right. In science, when we talk about a particular system in two different conditions, we usually refer to those two different conditions as states. So I'm going to use that terminology here. And I'm going to say one of the first things we want to do is break this up into our two different states, right? The first one, we're told that under one set of conditions, it has 2.7 gallons of gas and it can drive 56 miles, right? So this is our first set of conditions. That's state 1. And then there's a second set of conditions in which it has a full tank of 16 gallons. This is state 2. So the first thing we want to do is break those out and identify which things refer to state 1 and which ones refer to state 2. Okay. Then once we've done that, we can write down all of the variables for each state and the equation, right? So we know that these two things are proportional. So for state 1, the distance in state 1 is equal to the constant times the amount of gas in state 1. Distance for state 1 is 56 miles, and the amount of gas in state 1 is 2.7 gallons. Right? Then we do the same thing for state 2. Again, we've got the same equation, but now I'm going to write D2 is equal to K times G2 to indicate that those are the variables for state number 2. Now, in state 2, we have two unknowns. We don't know K, and we don't know D, although we do know G, which is 16 gallons. So the way the two-step solution works is what we're going to do is use one of the states, usually state 1, right? In state 1, we've got three different things. We know two of them. We want to solve for the third. We can use D1 and G1 to solve for K. And then because K is a constant, once we determine K from state 1, we can just put that over here. We know that's going to be the same K in state 2. We can use that newly calculated K to solve for the unknown variable in state 2. Okay. So let's look at state 1. Our goal is going to be to solve for K. So we can write D1 equals K times G1. That's our algebraic statement of the direct proportionality. And then we just rearrange this algebraically. We can do that by dividing both sides by G1. And that gives us D1 over G1 equals K, right? Or K is equal to D1 56 miles divided by G1 2.7 gallons. And when we do the math on that, we find that K is equal to 20.74 miles per gallon. The data given to us was only in two significant figures, so we'd probably round that to 21. If that was our final answer, we'd round it to 21. But since that's not our final answer, we'll go ahead and keep a couple extra digits and just use this line here to remind ourselves that that value is only precise to two significant figures. Now that we've got the value of K, we know that this value of K applies to state 1 and to state 2. So now we can use K to find out our final answer. All right, so let's finish this one up. We said at the outset we were going to work with this equation. D is equal to K times G. And for the second set of variables, we can put in subscripts here, 2, right? In the first half of the two-step equation, we solved for the value of K. So now, in state 2, we only have one unknown, which is D2. So we'll just put our values in and solve for D2. Sometimes you have to do a little bit of algebra to rearrange here. If, for example, if we had D, but we're solving for G, then we'd have to do a little bit of algebra to rearrange this. In this particular case, we've already written it in such a way that we can just solve for D2 directly. Okay. So D2 is just going to be K 20.74 miles per gallon times G, which is 16 gallons. Remember, that's only good to two significant figures. We multiply those, we get 331.85 miles. And notice that our gallons canceled here, as they should. Since we've only got two significant figures in all of our data, we should round that answer to two significant figures. So the distance is 330 miles. All right, so it's a two-step solution. Took us 2 steps to do it, but each of the steps were really pretty simple. We're just working with this really simple algebraic equation. So a pretty quick solution, even though it takes 2 steps. All right, now let's look at the second solution using isolation of constants. Now, when I teach this in class, I almost always use this 2-step solution because it's a little bit simpler. The isolation of constants is slightly, not much, but slightly more algebraically complex. And so I don't always do this. But if you can work your way through isolation of constants and understand what's going on, one, you'll see that it's a really powerful and efficient way to solve these kinds of problems. That's one thing. The other thing is textbooks often solve by isolation of constants, but they do it without showing you all the steps. They just kind of jump to the end and sort of throw it at you, and it's a little bit weird, and it ends up looking like something that you have to memorize because they don't really show you how they got there. They don't show you the ideas behind it. So that's what I'm going to do here. I'm going to show you how isolation of constants works, and we'll try it on the simple problem, and then we'll be able to use it. We'll have it in our tool bag so that we can use it later. All right, if we've got a situation like this is the same problem we had before. A car travels 56 miles on 2.7 gallons of gas. We want to know how far it'll go on 16 gallons. We've got the same set of algebraic equations describing state 1 and state 2. What we're going to do is we're just going to take these equations and put all the variables on one side and the constants on the other side. So for example, for state 1, we've got D1 equals K times G1. We want to put the constant on the right, get all the variables on the left. We can do that by dividing both sides by G1. And if we do that, we get D1 over G1 equals K. We'll do the same thing for state 2. We've got D2 equals K times G2. And if we want to get the constant K by itself, divide both sides by G. This gives us D2 over G2 equals K. But now here's the cool part, right? That part was simple so far. But if D1 divided by G1 on the left over here, if that equals K, and D2 over G2 also equals K, then it must be that D1 over G1 and D2 over G2 are equal to each other. And this is what the textbooks often show. The textbooks often just jump right to this equation without showing you the conceptual process for getting there. And that I always find that irritating. So anyway, for isolation of constants, we take both equations, put all the variables on one side, put the constants on the other side, and if this collection of variables and this collection of variables are both equal to the same constant, then those two collections of variables are equal to one another. And this gives us a new equation that we can use to solve for whatever it is we don't know in state 2. All right, so in solving with isolation of constants, we use the two simple equations to derive this new equation. And notice also that in doing that, our k's essentially just canceled out, right? They become irrelevant. We don't even need to worry about them anymore. That's why isolation of constants is a little bit quicker. It's a little bit more efficient. So now, since we don't need to worry about the k's, the only thing that we don't know is d2. That's our only unknown. And so we can just take this new equation that we've got here. If we want to solve this for d2, we want to get d2 by itself. We can do that by multiplying both sides by g2, and that will give us d1 times g2 over g1 equals d2. And if we put our variables in there, d1 is 56 miles, g2 is 16 gallons, and g1 is 2.7 gallons. Right. Notice that our gallons cancel out. Whenever you're doing math, please include your units. Including the units is really a helpful way to make sure that you've done everything right. If you do that and your units don't cancel and you don't get miles, right, then you've got to have a mistake somewhere. So seeing that our units cancel and we get miles, that tells us that probably all of our algebra is correct. All right, plug this into your calculator, and when you do, your head's going to explode. You won't believe what you get. You put that in the calculator, you got 331.85 miles, which was exactly the same thing we got last time. And so distance that we can travel, we'll say the same thing with significant figures. We've got two sig figs and all of these things. So the distance that we can travel is 330 miles. All right. In the study guide, there are a couple of problems that ask you to solve proportional and inverse proportional problems. You might try doing them once by the two-step method, and then try them again with the isolation of constants. Give them both a shot. See if you get the same results. If you do it two different ways and get the same result, it is amazingly satisfying. It feels so good. So I would encourage you to do that, partly for the educational benefits, but partly just because it feels really great to do that. All right, a quick caveat, which means a warning, right? A quick warning for direct proportionality. In this problem, we had a car. We're talking about the distance it can travel on a tank of gas. And when we did this, we said the distance you can travel is directly proportional to the amount of gas. And based on that, we came up with this equation. Distance equals k times the amount of gas. And that's perfectly reasonable, and it works, right? We just showed you that it works. We could have said the amount of gas that you need is directly proportional to how far you want to go. And if we state it that way, we could have come up with this relationship. The amount of gas is directly proportional to the distance. Okay. Now, both of these statements are true. That's good. And this one, give that a big check mark. That's good. Okay. You can use either one of those equations to solve the problem. The caveat is, the warning is, if you use this equation for state 1, you also have to make sure you use that equation for state 2. If you use this equation for state 1, you got to make sure you use that equation for state 2. Okay? And the reason is that even though both of these equations are true, these two k's are not necessarily the same. Okay? In fact, in general, they're going to be different. So you can write the equation either way. You can say y is proportional to x or x is proportional to y. Write it either way, but whichever way you do, make sure you stick to that for the duration of the problem. Okay? That's the important caveat for direct proportionality problems. All right, so let's look at inverse proportionality. Inverse proportionality is very similar to direct proportionality, except for an increase in x leads to a decrease in y. So what this means is that, excuse me, excuse me, if x doubles, y reduces to 1/2. If x is tripled, y goes down to 1/3 of its original value. Okay. A couple of examples: the number of people required to complete a job. So, for example, if it takes one person an hour to paint a fence, if you get 2 people, then the fence can be painted in half an hour. You've got twice as many people, the time required is cut in half. Okay. There aren't quite as many inverse proportionalities in relationships in science. They're a little bit harder to come up with, but there are a number of them, and there definitely are some that are important in our gas laws. So we're going to look at some of those. Well, first let's practice. Let's practice one of these. Okay, so we said that two things are inversely proportional if an increase in x results in a proportional decrease in y. We can, just as we had a graph for direct proportionality, we can have this graph for inverse proportionality, and you can see that what's happening is that as x increases, as we move in that direction, y decreases. So we can write this mathematical statement this way: y is proportional to 1/x. That's the same proportionality symbol that we used before. Or you can write it this way, and again, this is the more useful algebraic statement. Y is equal to some constant times 1/x. So if you can recognize an inverse proportionality in the relationship between two variables, then you can automatically write that equation, and with that equation you can solve any problems that you've got. Okay, so here's a simple inverse proportionality example. It takes 3.5 hours to drive from Lynchburg to Washington, D.C., traveling at an average speed of 55 miles per hour. How long would it take to get there on a high-speed train traveling at 145 miles an hour? Well, I hope it's intuitively obvious that if you drive twice as fast, or let's hope you're not driving that fast, if you're traveling twice as fast, you can get there in half the time. So the time required to get somewhere is inversely proportional to the speed of travel. And if time is inversely proportional to speed, then we can write an equation that looks like this, where t is time, k is a constant, and s is is speed. Okay. Then we can look at these at the data that's given to us, and we can identify data that corresponds to state 1 and some other data that corresponds to state 2. And with that, we can write our equations and list all of our variables. And once we've done that, we can approach this in one of two ways. We can try the two-step equation, or two-step process, or the isolation of constants. So let's try both of those on this. Okay, for our two-step solution, remember our goal is going to be to use the parameters for one of the states to solve for k, and then once we know k, we can use that k and plug it in for the equation for state 2. So To solve for k, we start with our equation. T is equal to k times 1 over S1. To solve for k, we multiply both sides by s. So we get T1 times S1 equals k. 3.5 hours times 55 miles per hour, and our hours cancel out, and we get 192.5 miles. Okay. And again, all the data is given in 2 sig figs, so that number should really only be considered. Let's remind ourselves that this is k. Okay. All right. So there's k. Now let's use that to solve for the missing values in state 2. All right, for state 2, we can use the same algebraic equation, except that we're going to include 2's for our subscripts here. T is equal to k times 1 over s, and k we already figured out using state 1 data. K is 192.5 miles, and that's the same value for either state 1 or state 2 because k is a constant. And now, again, sometimes when you get here, you have to rearrange this algebraically to solve for the variable that you're looking for. In this case, we don't, because we're trying to solve for t. So just put this here. T2 is equal to k, 192.5 miles, times 1 over S2, 145 miles per hour. Now let's look at the units here. We've got miles here, and we've got miles in the denominator here. So those two cancel out. Hours are in the denominator of the denominator. And when units are in the denominator of the denominator, that puts them back into the numerator. So that means our result here is going to have units of hours. And that's what we expect because we're trying to calculate a time. If we plug this into our calculator, you get 1.328 hours. And since we've got 2 significant figures in all of our results, that tells us that the time required to get to Washington, D.C. on the high-speed train would be 1.3 hours. All right. Now let's try the same thing with isolation of constants. Okay, let's tackle the same problem by isolation of constants. Start by writing our algebraic equations. And we'll write the equation for state 1 and the equation for state 2. Oops, there needs to be a 2. And then we just want to isolate the constants, right? So if we want to get k on the right side all by itself, we can do that by multiplying both sides by s. So if we multiply, in this equation, we multiply both sides by s1, we get t1 times s1 is equal to k. And for state 2, multiply both sides by S2. This gives us T2 times S2 equals K. And if T1 times S1 is equal to K, and T2 times S2 is equal to K, then those two things must be equal to one another. So we get T1 times S1 is equal to T2 times S2. And again, this is the form that you'll often see these equations in the textbook, but they skip all of this stuff. And it's really difficult to remember when the equation has this form and when it has the form that we had before for direct proportionality. So the best way to do this is not to remember the different equations, but just understand direct proportionality and inverse proportionality, and then derive this yourself based on these fundamental equations. All right, so now having gotten this, let's go ahead and continue to the solution. All right, so we just figured out the correct algebraic equation to relate the variables of state 1 to the variables of state 2. We got T1 times S1 equals T2 times S2. And again, just as before, when you do isolation of constants, the constants disappear and they don't matter, so we don't need to worry about K. The only thing we need to solve for is T2. So we look at this equation here. We want to isolate T2. We can do that if we divide both sides by S2. So this tells us that T1 times S1 divided by S2 is equal to T2. And so T2 is equal to T1 3.5 hours times S1 55 miles per hour divided by S2 145 miles per hour. And if we look at our units, we can kind of group them. In this case, we've got a miles per hour here and a miles per hour here. We can just go ahead and cancel that whole part in both cases, and that leaves us with hours, which is what we expected. If we put this into our calculator, again, we get exactly the same thing we had before, 1.328 hours. And we give a little bit of thought to our significant figures, and our final answer is 1.3 hours. All right, pretty simple, I hope. All right, so in this video, we looked at direct proportionality, which says two variables x and y are directly proportional if a increase in x results in a proportional increase in y. And we said that the algebraic equation to relate those two is y is equal to k times x, where k is a constant and k is also the slope of that line. We've also got inverse proportionality, in which an increase in x leads to a proportional decrease in y. And we said that the algebraic equation that relates variables x and y is y equals k times 1 over x. And again, k is a constant. Then once we looked at those and showed how if you can identify direct proportionality and inverse proportionality in the relationship between a couple of variables, then you can use these two equations to solve for anything that you don't know in that set of parameters. And we looked at two different ways of doing that, the two-step solution, and isolation of constants. And we also said that it is a heck of a lot of fun to do it both ways and see if you get the same result. So I would encourage you to do that. It's intensely gratifying to do a problem in two different ways and get the same result. It's also good practice. All right, so work on those. There are some study problems on direct proportionality and inverse proportionality. And in our next video, we'll look at applying those to the state variables of gas laws.